Welcome to this presentation in which we will show an identification example. We will demonstrate the two-step procedure and then we will simultaneously determine the parameters and then we will do this through an example also present as Scilab code. Recall the earlier example, we already saw this about 2 lectures ago. We generated data using the following model with the intention to fit a model with the data. We determined the impulse response coefficients and we obtained one sample delay. It is 0 here, non-zero from lag 1 onwards. So we fitted with the smallest model for B and F with one coefficient each. We obtained the following fit. I have now written that in the form of mathematical equation. You can see that 1.441 here and 1 minus 0.7136 here, and there is one delay, so we have denoted as U of n minus 1, and then white noise C of n, and this is B by Q, this is B by Q. And then we checked whether the residual yn minus y hat n given n minus 1 was white. So we found the ACF of the residual. We can see that the top plot, that is the ACF plot, is not impulse, it decays slowly, it is not white. Because it has an exponential delay, we said possibly we could model this noise as AR. This is based on the discussion we had for AR modeling. And then here is the Scilab code that is used. So we took this, the residual yn minus y hat n given n minus 1, and notice that we have a non-zero at lag 1 and 0 for all other lags. So we say that perhaps AR1 model may be tried. When we fitted the noise, that is the residual alone, we get the following expression which I have written here. You can see here 1 minus 0.8771, it is in the denominator. This is the one we obtained just now. But these two transfer functions have been calculated in 2 stages. As a result, there could be some questions about consistency and so on. So as a result, we determine all parameters simultaneously with these parameters as initial guess. With this, we obtained the whole transfer function. You can see that B is 1.341 and it is given here, and it has a delay of 1, z power minus 1, so I put U of n minus 1 here. The denominator here is F, and that is 1 minus 0.7395, which I have taken here, and finally 1 over D, D is given here 1 minus 0.8906 z inverse times Cn. We call this model as Bj1. This is the first model that we have determined by fitting all the parameters simultaneously. So we have to check for the whiteness of this residual. This yn is the data that we were given with. The second term is the prediction by the estimate, and we obtained ACF and CCF of the residual of Bj1, what we mentioned in the previous slide. We see the ACF to be white, it is 1 here, 0 everywhere else, but CCF is not 0. You see that it is going outside this yellow box. Because noise is not captured, we increase the order of F and try again. So we increase the order of F and try again, and we get the new transfer function as given here. So we have an extra term here which is given here, and of course all parameters have changed. We have simultaneously fitted all parameters by asking the Scilab code to increase the model order by 1 in this polynomial. So once again, for this new model which we called as BJ2, fitted the transfer function. So we have now ACF1, that is impulse, and CCF absolutely 0. So we can say that we have arrived at the final model. Let us summarize. Here is the data that we generated with. Remember, we used PRBS, we used white noise here, and then we got this output. We call that as Y. Then the first guess we obtained by the two-step method. We determined this first, and then we found that the residue was not white. We fitted that separately, we got this transfer function. Then we fitted it simultaneously, we called it the BJ1 model, and we found that ACF was impulse but CCF was not 0. So we increased the order of this and we obtained the final model. This gave ACF to be impulse and CCF to be 0. So this is the final model. We can stop here. It meets all our requirement, and you can also see that this is very close to what we started with. So here is an example of a more difficult problem with a more detailed noise model. We can use this procedure to identify data obtained from a plant whose transfer function is not known. The method is very similar. It is extendable. Using the Scilab code, you can apply this to many more realistic problems. As I mentioned earlier, this is an extremely important subject, a practical topic, very useful in applications. The identification method helps reduce the time required to arrive at models. These are the models that we use for control system design. I would encourage you to try out the Scilab code. Make sure that you can reproduce all the models shown here. Of course, there could be slight differences because the PRBS generated in two systems could be slightly different. As a result, all the models could be slightly off, but only slightly. With this, I would like to conclude the important topic of identification. Thanks for joining. Goodbye.